Okay, before we move on to uh, infinite systems like waves, we wanted to recap all the things we have learned so far. We have learned free, and next will come forced vibration. So the first thing we learned, if you recall, is simple harmonic systems, simple harmonic oscillator. There are many examples. It's one of them. One of them is a mass attached to a spring, and there's the equilibrium point, and we have x-axis, and this distance is x as function of time. So x is the dynamical variable, so it has a but this is not the only system. You saw other systems which behave this way, behave in a simple harmonic oscillator way. All of them have 1 degree of freedom for us. So we just did 1 degree of freedom. You can have simple harmonic oscillator with 3 degrees of freedom, but we did 1 degree of freedom. And a dynamical equation, our so-called equation of motion, is this is the equation of motion that you get from Newton's second law. And here you get d square x dt square equals to minus omega square x. In this system, in this system, omega square is k over m. If you have a pendulum, in a small oscillation of pendulum, it is L, and omega square is g over L. Other systems will have related to other properties, but all have this kind of equation where will be you have a dynamical variable is proportional to itself, and there's a negative sign, and this is a positive number. This is positive. So there's only one mode. You might say that's the normal mode for this thing. There's only one mode. So one frequency, one mode, and so the solution is so first thing is frequency of this mode, frequency omega, which angular frequency is called k over m, this angular frequency. And the mode solution is x of t is made up of cosine of this oscillation and the same, and there's some unknown constants which are determined by initial condition. Initial conditions, which are x of 0 and v of 0, with v is dx. Okay, so this is a simple harmonic oscillator. Okay, so the second type of system we did was two independent two simple harmonic oscillators. what do I mean by this? By this you mean something like this. So you have this, and you have one pendulum, and you may have another pendulum of a different length or same length, but they're not coupled. So this one goes with omega 1, and this one goes omega 2, and so you have two separate things. So equation of motion will be d square, let's call this A, call this B, so xa dt square over its own and d square xb dt square equals minus omega b square xb. There is no other term here. A is not doesn't depend on b, and b doesn't. So this is kind of like its own oscillator. This is separately. This will be xa will be like that, and xb d will be like that. So if you write that down, xa will be some a cosine omega at plus ba sine omega at, and will be some constant cosine omega bt plus bb sine omega bt. This is not surprising, right? This just they're kind of separate. As if, for instance, I could have another one like this. This is A. This is B. So this one is going with omega A, and this is omega B. There's nothing, no coupling. So this is a very nice two independent simple harmonic oscillator. And third thing we did was coupled systems. Two linearly coupled oscillators. Well, this is we did several examples of this. This is actually the main thing Virus and Waves course. So one of the examples was, well, if I have the same system as that, I have A here, B here, so this guy is XA, and there was some equilibrium over here for B, this XB, and we have a couple, there's another spring that couples them. So now it's coupled. A and B will depend on each other. And if you look at, this is an example of a system. You could have two pendulum coupled like that. So basically you have two oscillators, this oscillator, and somehow they're exchanging energy with each other. There's a mechanism for exchanging energy with each other. And in a this still is a conservative force, and it linearly depends. So equation looks like d square xa. So if I look at the dynamics of this guy, then I get some number here which is restoring for omega a square xa. So it's kind of like that in a way, if there was no coupling, and then because there's a coupling, there's a depends on xb. So let's call it omega c is square xb. So we just give some number there, and we derive this using Newton's law, but I don't want to get detail of that. And if you look at this guy, because this comes from force of B on A, I'm going to get exactly same thing that on B by A. So let's call it omega C, and so omega C square XA, and this may have its own spring constant, so its separate frequency will be different. Omega say B square XB. So an example of something like this may be, let's see, I worked out some numerical example earlier to share with you. I'm going to find that numerical example. So an example may be d square xa dt square equals minus 3xa plus xb, and d square xb dt square equals to xa, so same coefficient, minus say 5xb. So an example like this. So over here, what we have is we can't really solve it like this problems. So we do it what is called method of solve by method of normal modes. So I'm going to take this in the next on the next page. So we have two linearly coupled oscillators, and an example is this. Other examples are that we have encountered is we take a pendulum, take another pendulum, they're independent of each other, but then we put a spring between them. So maybe Kc, and this is L, L1, L2, maybe same L, M1, M2s are different maybe. So you have systems like this. An example, numerical example will be something like this. If you were to solve XA and XB, you don't get XA equals to some A cosine omega t plus B sine omega t. You don't get XB some C cosine omega t plus D sine omega t. And the question is, because these omegas, we don't have omegas, so these omegas, you have a problem. It turns out, because this is a linear system, we can do what is called method of normal modes. So method of normal modes does not solve x and xb directly, but it tries to figure out the frequencies and the pattern of the motions that will occur if it was in a special frequency. So there are some special frequencies. So some special frequencies. And pattern among displacements, among motions of the two. Okay, so I don't want to completely go over all the problems, but how to do that, and it is done separately in another place. So what we do is find we demand that there are special motions, simple harmonic motions. So, which means we say XA is going to go with some amplitude A cosine omega t, and XB would go with some B cosine, and we demand that this be the same. So we demand this, that we're looking for this. We don't know what A and B's are, and we don't know what omegas are, but we're looking for this. So we can work with this or work with this. Let's work with these two equations for simplicity into 1 and 2, and we discover that it is possible, as long as A and B and omega satisfy this, omega squared minus 3A plus B equal to 0. So this is 1 prime, and another one is A plus 5B equal to 0, 2 prime, right? So as long as they satisfy, if you say, okay, how about A is 0? If A is 0, then of course B is 0, and this is fine. A equal to 0, B equal to 0, always a solution. But this is called trivial solution, right? And we ignore this. Because we're looking for motion, and we're not looking for them not moving at all. This, if A equal to 0, X will always 0. So they basically is sitting at equilibrium. So if A and B not equal to 0, A not equal to 0, and B not equal to 0, that actually means that the determinant of their coefficient matrix, omega squared minus 3, 1, 1, omega squared minus 5, that has to be 0. If this, then I must have that 0. So when you expand this is omega squared to the square minus 8 minus plus 8 omega squared plus 14 equal to 0. So if you say omega squared is x, this is quadratic equation. So it's x squared plus 8x plus 14 equal to 0. And that can be solved for x is 1 over 2 minus 8 plus or minus square root of 8 squared minus 56. So this says omega square is going to be two values. It's minus 8 here, minus 8 here. So this plus 8 here. Mistake over there. So two values is going to be 4 minus square root 2 and 4 plus square root 2. Two values. So we just call it this omega 1 square. So we just say omega 1 square is 4 minus square root 2. That means omega 1 is, and we just keep the positive root for positive frequency. And omega 2 square equals 4 plus square root 2, and omega 2 is plus square root of 4 plus square root 2. This is very common solving these problems, square root of square root, you know. Okay. so we have two values, and so when omega equals omega 1, that's one case, and then we have when omega is equal to two cases. So these are called eigenvalues, and we want to find out what A and B will be. If you look at this, actually they are not independent. If omega 1, this is omega 1, then there is a relationship. But they will give you the same relationship. So you can just pick one of them. So let's call it omega 1 square minus 3. Let's call that A1, and the other one is B1 equal to 0. So this tells me what B1 and A1 related. So we can say B1 over A1 is going to be 3 minus omega 1 square. So 3 minus 4 plus square root 2. So this is actually minus 1 plus square root 2. When omega equals to omega 2, we will have omega 2 square minus 3. Let's call this value of A in A2 plus B2 equal to 0. So B2 over A2 will be, if you this will be 3 minus omega 2 square, so 3 minus 4 minus square root 2, and that makes it minus 1 minus square root 2. These are called Eigen Vectors, but these are actually ratios that go into Eigen Vectors. So if sometimes people write it like this, A1 and B1 values. So if A1 is 1, B1 will be, so this will be, if I put A1 is 1, then B1 has to be minus 1 plus square root 2. So then in writing this way is called eigenvector for eigenvalue omega 1. Our mode for frequency omega 1. Okay, and so this one can be similarly, if A2 is 1, B2 has to be minus 1 minus 1 minus square root 2. You can see that there is I could have multiplied, I can pick any values. So this whole thing is off by some kind of constants. If I put some C here, this will be this times C. I'm not going to worry about that. So these are, okay, so let me summarize here. So we have two solutions, two normal modes. One is omega equals to omega 1, and in that case I have a solution. I'm going to call it Q1, and that will be the A1 go with XA, so this is XA, and the B1 part go with XB plus minus 1 plus square root 2 XB. When omega equals to omega 2, then we say we have this thing moves, so these are functions of times, right? So it's telling me how this will move. Q2t wasn't right like this. This again, this will go with XA, and the next one XB. XAT plus minus 1 minus square root 2 XB. Actually, you can show that if I do d square q1 dt square, then I get minus omega 1 square q1, which is minus 1 omega 4 minus square root 2. So this is minus 4 minus square root 2 q1. You can show that similarly for d square q2 dt square minus omega 2 square q2 minus 4 plus square root 2 q2. So these are the these are normal modes. They are not the full solution. They are not telling me what XA and XB are. They're just telling me what Q1 and Q2 are. They're also not telling me if I start out some arbitrary points in A and B, where they will be at different times. So these are called Q1 and Q2 are called normal coordinates. So far, just we're working out mathematically some special types of motions. So if somehow I started out in this fashion, I will stay in Q1 because Q1 doesn't know Q2. Q1's motion is completely determined by Q1 itself, and Q2 completely determined by Q2 itself. So I'm going to now, in the next talk about how to address the question of the motion of A and B themselves if I know what the normal modes look like. That's the next one. Okay, so we had a system XA double dot equals to minus 3XA plus XB, XB double dot equals to XA minus 5XB, and this one we found out omega 1 was a square root of 4 minus square root 2, and omega 2 was square root 4 plus square root 2, and when we look at B over A ratio for when I'm in here, then this was minus 1 plus square root 2, and B over A ratio when I was in 2, it was minus 1 minus square root 2. So these are the normal modes, and using these guys we could write Q1 would be XA plus this B over A minus 1 plus square root 2 XB, and Q2 is XA minus 1 minus square root 2 XB. So this is B over A, this B over A in this mode. And you were to show using these guys over here, just use a Q1 double dot and you process the algebra, and it is a little bit of algebra, so you got to do it. You would get minus omega 1 square Q1. So this, like, Q1 is a simple harmonic oscillator. Like, this combination of A and B is a simple harmonic oscillator, and Q with frequency omega 1, and Q2 double dot is minus omega 2 square Q2, and Q2 is a simple harmonic oscillator also. So that's the meaning of the normal modes in a way. Okay, the system we're talking about is, just to remind you, an example system would have been this. Right, so from there these numbers were obtained, and then I'm processing like that. But ultimately our goal is that this is XA, this is XA, and this is XB. So I mean, if I have this system, what I'm trying to do, well, I would like to know if I have any arbitrary way I start it, where they will be at any other time. So the goal is starting with any arbitrary situation. What the meaning XA0, XB0. So those are the positions where they started. And not only position, I could have started with a kick, like kicked A or kicked B. So they could have started with the initial velocity. So VA0 and VB0. So these are the initial condition. Where will they be at any arbitrary instant later? So that's the goal. I should be able to study the dynamics of this completely. So we said, okay, XA, I can't solve this directly like I could do for one of them. If there was by itself there was no such thing, I could do it. When these guys were not there, I could do it. But they're there, I can't do it. So I get the normal modes, and I see the normal, if I get the Q1s, they are easy to solve. And Xn, Xb, Q1 related to Xn, Xb. So let's see, I'm going to call this equation 1, equation 2, and 3, and 4. So my thinking would be, we know 3 and 4, so solve 3 and 4, and put into 1 and 2, and find out X and XB. So the strategy is, solve 3 and 4. So step 1. Step 2 will be, step 2 will be, put them in 1 and 2 and solve them for XA and XB. Makes sense, right? So if I solve like 3 and 4, let's see what 3 and 4 solution looks like. 3 and 4 will be very easy to write down because I already know the answer to 3. So 3 will look like, what do you think the solution of this guy looks like? Well, that one is just same as any harmonic oscillator. Simple harmonic oscillator. This same as this guy. So it's going to look like that, except omega will be omega 1, right? So that's simple harmonic looks like this equation. So this is going to be the same. Always simple harmonic oscillator, we're going to have the same equation. So I'm going to have Q1, I'm going to get not X, but Q1 would look like some constant A cosine omega 1t plus some constant B sine omega 1t. Of course I could use phase, but I'm going to just do sines and cosine. The 4 look like, what do you think this 4 will be? Any idea? I'm sure you've got the idea of Q2 will be. Well, Q2 is its own word, so I don't think there are going to be A's and B's. It's going to be some other things. Let's call C cosine omega 2t plus D sine omega 2t. Now you can see that these are the only unknowns now, A, B, C, D, and we have how many conditions? We have 1, 2, 3, 4. Those 4 conditions will be sufficient to nail these guys down, and that's the ultimate solution, right? So, okay, let's see. I'm gonna put so I've done this, so I've got the solution and put into 2. Rather than put all of this thing right there, I would say why not first solve for Q1 in terms of Q1 Q2 rather than have much more complication. So I have an XA plus, let's call over this guy over here, this guy over there, I'm going to just, rather than carry all of this over here, let's call this little a and little b. So I can just write down in terms of little a, xb equals to q1, and xa plus little b xb is q2. So to get xa, I need to get rid of xb's. So this times b and this times a, and then I subtract it. So I get that gives me b times xa, and a times gives me b minus a xa. It will cancel this guy out. It will give me b times q1 minus a times q2. So xa will be b over b minus a q1 minus a over b minus a q2. Alright? So these are all known. These are gonna have some values. I'm not gonna worry about it. We might just say, let's call this guy some other symbol, so alpha and beta maybe, you know. So this is like a alpha 1 q1, alpha a q1, include minus in there, plus beta a q2. So alpha a and beta a are known. How do I get xb? I'll just have to subtract xa. So I'm going to subtract xa. So let's say subtract this guy from here. So these guys are not there anymore. Subtract, so b minus a xb will be q2 minus q1. So the xb is going to be minus 1 over b minus a q1 plus 1 over b minus a q2, and we can call it this guy alpha b and this guy beta b. So we got xa is alpha a q1 plus beta a q2. Okay, what's my task to you? Task for you is carry out the numerical values as I show you the pattern in which the calculation goes. Alright, so xa is this, and xb is alpha b q1 plus beta b q2. Well, if q1 and q2 are, you know, I can put in there, and you can see now this just turns out to be alpha a times a. Let me write that down. Alpha a times a times cosine omega 1t, cosine omega 1t, plus alpha a times b, sine omega 1t. So this is all from first mode, and second mode beta a actually c, beta a c, the q2 is going to c cosine omega 2t. This is beta a with c and beta a with d. Beta a with d sine omega 2t. Okay, so and this one say what the xb will be. xb will be alpha b q1, so a cosine omega 1t plus alpha b sine omega 1t plus beta b c cosine omega 1t plus beta b d sine omega 2t. So only thing, now notice that the only thing we don't know in this, so this is XA and this is XB. So these are the only things we don't know. And they're the same over here also. So they're the same. And we have, so how do I get them? We get them using these initial conditions. So initial conditions to fit are XA0, XB0. So let's call it, so if I put XA0, this gives me, this will give me XA will be alpha A plus beta AC, because these guys will be 0, and this is going to be alpha B A plus beta B C. So I will be able to get A and C from there. So A and C will be, so get A and C. I don't know what B and D will be, and that one has to be use the velocities. So to get the velocities, I need to convert this. I need to take d dt to get VAT, and this one d dt will give me VBT. And so now I can use VA0 and VB0, and you will see that it's going to be omega 1 alpha AB, omega 1 alpha AB, because this will get 0, and it's going to plus omega 2 beta AD, and this guy is going to give me omega 1 alpha BB plus omega 2 beta BD, and so these guys will give me B and D. So you can see, carry this out, you can take particular values for this. Maybe you can call 2 and 3, and maybe this guy 1, and maybe give it some unique value, maybe 4 or something. So carry this out for the example that you have at hand and see what you get. This will give you a complete picture of how to handle arbitrary situation when you have already figured out normal modes. If you haven't figured normal modes, you just know this. You have to go this route, and then you have to use this strategy over here in order to proceed. Okay, I'm going to stop this thing, and then we're going to do finite system, continuous finite system. Okay, let's see. By finite system, I mean that there is a length over which the system goes. If this length was infinite in open space, we'll have a separate consideration. But this is a finite system. It has normal modes of vibrations, which are called modes, just modes here. It is continuous, meaning at every point there is a particle that makes the number of particles infinite. So you have infinitely many oscillators. So each point, so if I go say this was the x coordinate, and over here, then so we have oscillation of this guy, and if it's over here at time t, this displacement is my variable. Sometimes you have like a closed tube, and if you're looking at the velocity as a displacement, you are going to get a same kind of both ends fixed. If you're looking at pressure from the ambient pressure, difference between the ambient pressure and over here, so an open tube with a pressure as a as a displacement variable, then you get the same situation at both ends fixed. So displacement, we've been using y of x and t as a y coordinate like this, or we can do psi of x t. So this is a displacement of particle at x by the amount that's the displacement. So this is the y coordinate. So this here is y coordinate of the particle at x. Right? So that's the displacement in this system. Okay, so we know that this system, this will be a particular system, will be similar over here. The dynamics is dynamical equation of motion of the psi xt. Okay, so this variable is classical wave equation. That the dynamics is contained in that, and that's a d square psi dx square equals to v square of d, let's call it dt square v square d square psi dx square. You can write another way. You can write d square psi dx square is 1 over v square d square psi dt square, either one of them. What is v? V is related with the, in this case, property of tension and mass per unit length. So T is so V is equal to square root of T over mu, and in general is a square root of some tendency that's kind of trying to restore the system, and mu is a inertia. So there's a two tendency, restoring tendency, reaction to the displacement. Okay, so another one is inertia. So in different system, for instance, in the case of pressure, this will be a pressure, not tension, and inertia will be the density. This will be density, not mass per unit length. But you have to study each system and then find out what's the corresponding thing in that system for the V. Okay. So both end fixed means psi of 0 t is 0 and psi of L t is 0. So when you try to solve this problem, it's actually not solvable directly, right? So we solved it in a different way. So if you look at the coupled versus uncoupled, what this system is actually has infinitely many, not just two. In this system you had two. You had these two guys coupled. Here you have infinitely many, has infinitely many linearly coupled oscillators. So it's kind of like a dag on asteroid. So it's like not just two, you got infinitely many, whole bunch. So how do you do it? Well, the same way, even just for two, you had to go to normal modes. And for many, of course, you're going to have to go to similar kind of route. So we do normal modes, okay? That means go the path of normal modes. Well, here it's it turns out to be a product solution. So that means that will mean find a special mode frequencies and B over A analog of that in each mode. The B over A was okay if you just had two particles. The B over A here turns out to be a function because you want to know if I go over here in one mode and this guy is over here another place, so what's the ratio of that for every one of the pairs, right? So this turns out to be what we will call a mode shape, you know. So it will look like a mode shape instead of just one thing, and that's why it's a function. It's going to be a function. So instead of B over A, it's going to look like phi n of x, and mode frequencies will be omega n. So we need to have frequencies in this. With what frequency, what's the mode shape? That's what we want in this particular case, right? To figure out first the normal mode, not the solution. The full solution is I want psi. I don't want normal modes. These are just a way to. These are like cues. These are the analogs of the cues that go with each frequency. Not yet the psi. Okay. So let's see what found before that in when both ends closed, you have omega n equals v times kn, with kn equals n pi over L, where n equals to 1, 2, 3, forever, and phi n of x was sine kn of x. And this is not normalized. If it was normalized, if normalized, then we have a 1 over square root of L sine kn x over period 2L. This is normalized over a period 2L. We can work with this. Okay, so these are mode shapes. So if I'm in this mode, what the solution would look like. So those are the cues. So now to the q ends. Okay, so cues will look like if I'm mode 1, say n equals to 1, then my vibration will be sine k1x sum a cosine omega 1t plus sum b sine omega 1t. And I can just label the 1 here because if n equals to 2, I would be sine k2x a2 cosine omega 2t plus b2 sine omega 2t. These a's and b's, I have to figure them out by initial conditions. So, but these are all the q's right now, right? So this you may call it, I got a q1 of x and t, and this is q2 of x and t, and so on and so forth. So these are normal. If I'm in a normal mode, these will be the vibrations that I'll see. So if I started with this shape, this is what the future looks like. If I start with this shape, then this is the future that it looks like. But I have to start with a zero velocity for, if I start in this shape, is zero velocity, there's going to B's will be zero. If you start in this shape, but I gave it some velocity, then I'll have to figure out both A's and B's, what they look like. Okay. All right. So Q1, Q2, and so you can see n equals to m, some arbitrary one, I'll say k mx, some am cosine omega mt plus bm sine omega mt. Okay, so these are the normal modes. What I want to solve is, I have the normal modes, how do I get my psi? So problem to solve is, given psi x0, that's, I start out as some shape, so maybe I pull it over here, kept everything like this. Maybe I give this a velocity, so that's a psi x0, and then psi dot x0. Maybe if every place zero velocity, this has some velocity, and then this velocity, and then every. So given psi x0 and v, let's call that v, vx0, what will be psi x of t and vx of t at any other. So this is the problem I want to solve, but I found this. So this is, if you remember how the two body problem went, this is going to be exactly like that, and that's going to be next sheet of paper I'm going to work on to show you how to do this. Once I figured out these guys are just each of the normal modes, each of the mode shapes, and how, if I got them into mode shape, how future might look like. You can see the amplitude. This just basically gives the amplitude of the shape itself. All right. So I'm going to stop here. I'm going to continue the next video, because my videos don't go for too long. Okay. So we are here. Both ends are fixed case. So that's the example we're looking at is this system, and the length t, mu, length is L. Okay. So from the mode calculations, a separate calculation, right? We find mode frequency look like that. The case take this. It's very tied in with what happened in the boundary conditions. Answer this. And the V in this case is that, but in general can apply to the same thing, can apply to, for example, a tube that's tied at both ends, and there the speed, which is speed of the wave in this medium, is going to have something like this, some restoring tendency of inertia. The T is for restoring tendency, inertia is this mass related property. And these are the normal mode shapes. So these are the analog of B over A in two mode system. And so these will be the analog. I introduced this here because I feel you should know that this is the same thing in normal coordinates. So what we have is you might think, say if I'm in this mode, so I'm in one of these modes, then I'll have oscillate with cosine with this amplitude and sine with that amplitude. So alright, now I want to say address these questions. This is the physics question, the physical question, that I start out my string in a particular way. What the string will do at some other time, that's I want to predict, so I can go out and test it in my experiment. Okay, so we use what is called superposition, and that's what is Fourier series does that. In a way, it ends up with Fourier series. Right now, I'm just want to say adding up modes will give me any shape whatsoever. So we're going to use a principle that that comes from linearity of this equation from which this comes from. Okay. All right. Let's see. I'm going to claim that psi of x of t is just going to be not just any particular mode, but all the modes added up with amount that I need to add these are coefficients going to guarantee amount I need to add. So I'm going to have n equals 1, 2, 3. If I add up all of this, so this is I'm in nth mode, so at different x values I need this amount. There are b over a's ratio, so I'm in that mode, and then I don't know how much I need. So this will be the mode shape, so then claim that this is the mode shape, not mode shape, shape of a string. Shape of string at t. So that's what this is. Okay. Well, the velocity will be, I just take a time derivative of this d psi dt. That's just going to give me, derivative will go inside. Nothing happens here. Inside here, let's use this bracket. So omega n with a negative sign, and this goes into sine. So omega n bn, it's going to be cosine omega nt. Now I need to have a way to find an and bn. So an and bn will be obtained from using your initial conditions. So all right. So I do psi of x0. I'm just going to do psi 0 x, call that psi 0 x for simplicity. That should equal to, I put 0 there. Of course, b's, none of the b's are there, so this is just n equals to 1, 2, 3 sine. So this is an sine can x. That's all remain. Vx0, let's call this v0x. So this is some function given to me. And when I go in there, this goes away. Bn omega n Bn sine kn x. Well, these modes sine knx, sine kmx, they were to be over period 2L. If you remember, just in this system it was period 2L in this system. Now if I was one end closed and another end was fixed, another one not fixed, free to, so the derivative was vanishing there, the period will be 4L. So there's a difference in there. So if you have done this algebra here, this calculation here, this you found that this is actually 1 over basically square is L, n equals to m, and 0 if n is not equals to m. And that's why 1 over square root of L normalizes it. So I can play this trick. Let's say I want am, then I multiply both of these with sine kmx. So sine kmx, and then integrate, right? So multiply by this both sides and integrate. So I'm going to get on the left side it's going to be psi 0x times sine kmx dx 0 to 2L. Okay, and mind you, this is only known between 0 and L, only known between 0 and L. So what to do between L and 2L? Answer is up to you. You can just set it to 0, or you can, for the convenience of calculation, you might choose a more symmetric situation. But this should not make a problem for you. So on the left side, and on the right side is simply when n equals to m, and go in there. So I have a sum over n am, but this is sine knx. You can see multiplication and integration, they go through the summation sign, right? Sine kmx dx. And so this is going to be for only that value of n when n is equal to m. I'm going to get, and for that I'm going to get L for this, L times am. So this says am is 1 over L, and I need to do this integral. But I claim that this was this psi of x depends on not just a but also on b. So I need to find b also. I need to find b also. The b will be found through using this. So for the b, if the velocity was 0, say, if this was 0, and each one of it is independent direction vector, so to say, then you can see the b's will all be 0. If v0x equal to 0, then all the bn equal to 0. That's a simple case, right? But if that's not the case for all x, so it was 0 throughout everybody, so in this case, but if v0 is some function, then I do exactly the same trick. I'll get omega m dm is going to be 1 over L 0 to 2L v0x sine k mx dx. And this will give me what the BM looks like, so that I can make it over here BM. So that's my BM. So I got the answer, therefore answer, so psi of x t is over here, that answer. Hope this clarifies a finite continuous system. I've just illustrated for both ends fixed, but if other cases that I have not done that you should do as practice is one end fixed, the other end free, and third example is both end free. Okay, I'm going to stop here and try to upload these videos, whole bunch of series of videos in this review sessions. Okay, bye.